Welcome back. And today's question is a special one for many reasons. It used to be a question I used to start my year 9, year 10 maths lessons with, just to see how my students approach problems. It's a question that has a wonderfully nice answer, one of those answers which has someone that really enjoys maths, you'll sort of go, oh wow, that's really clever. I don't want to say anything else. Have a go at the question. Very rarely for me, I've also included a sneaky, clever way of doing the question as well. All I've shown you is you've got two semicircles inside a larger semicircle. I'm telling you one length is 2, and I want you to work out the shaded area. And those two smaller semicircles do not have equal radii. Good luck. Talk again in a minute. Okay, so how do we do? I will say, if you got the right answer, you'll probably know you've got the right answer because it just looks really neat and really clever. Let's have a go. So firstly, I'm going to amend the diagram like this. So sorry just to pop it up, but it's just easier just to do it in one go. So of the smaller inner semicircles, I'm going to give that a radius of r subscript 1. Of the larger inner semicircle, I'm going to give that a radius of r2. The very large semicircle around the outside, I'm going to give a radius of capital R. And then the x represents the shift along from the center where the vertical 2 line is, or the vertical line of length 2. And that just allows me to sort of frame the question. Now, what I'm really hoping for is I'm going to set up some equations, and I'm going to hope they all cancel out and fall out, and I'm just left with something that gives me ultimately the answer. So it's one of these questions that you kind of just have to do some maths and frankly cross your fingers a little bit. So let's start off with hopefully the most obvious thing, which is I can see I've got a right angle triangle. So if I set my right angle triangle up, I've got a height of 2, a base of x, and a radius of r. Now, as with all circle questions, the key is to try and find different radii which get you to various lengths. So I've used my big R here, and that tells me using Pythagoras that r squared equals x squared plus 2 squared, or in other words, r squared equals x squared plus 4. That's going to be my equation 1. Again, don't really know where I'm going with this. I'm just hoping it all cancels out somewhere because I have a lot of unknowns. The next thing I can notice is if I look down in the bottom left of my diagram, well, it must be the case that r, the big radius, so capital R, is equal to the 2 small radii of the small semicircle plus the value of x. So I've got another equation, which I'm going to call equation 2. I'm actually going to go a stage further and rewrite it, partly because I know where the question's going, and it allows me to squeeze it in slightly better. I'm going to rewrite that as an equation R1. So R1 equals half R minus X. And again, make sure you're okay with it, where that comes from. Similarly, it must be the case that if I add together the two R2 and R2, and then I take away X, that must give me the large radius. So in other words, again, very similarly, I can write big R equals 2R2 minus X, rearrange that, which gives me an equation in R2. So all I'm doing is generating some equations. Again, I know where I'm going with this, so it's why it looks like I've done it magically, but these are the equations I'm going to need. The next thing is a statement to the obvious, but actually it's often the thing that my students miss when I do this question. It's the really obvious one. 2r, so the base of the large semicircle, or the diameter if you like, so 2r is equal to r1 plus r1 plus r2 plus r2. So in other words, I can simplify that down to r equals r1 plus r2. So I've got 4 equations, which I hope are going to help me in some way. The next thing, as with all these questions, is to try and set up an equation which tells me the thing that ultimately I need. And I'm trying to work out the shaded area. So the shaded area is going to be the entire semicircle minus a small semicircle minus the even smaller semicircle, depending on which way you label your semicircles. So in other words, my area is going to be my large semicircle minus my small semicircle minus my other small semicircle. And I've rewritten that in a slightly factorized form, which is going to be pi over 2 r squared minus r1 squared plus r2 squared. Not obvious what's going to happen. And so I'm still, frankly, as often happens when you do these sorts of questions, I'm hoping something's going to work. Okay, so what I've now done is I've shrunk the diagram down and I've put those equations in a slightly larger font so you can read them more easily. So I have, again, equation 1, which is the Pythagoras, equation 2, 3, and 4, which is the various relationships of the radii. And then it's not technically equation 5, but the area equation, which is the large semicircle minus the 2 smaller semicircles, which I've then rearranged. Now, There are lots of ways to proceed here. So I'm not saying this is the only way, but this is the way that kind of fell out for me. So it's the way I'm going to show you. I've got r1 squared plus r2 squared in my equation. So if I look at my area equation, I've got, again, r1 squared plus r2 squared. This is really common when you do maths problems, where you're doing A-level maths or where you're doing sort of these slightly Olympiad type questions. That's really hard to deal with. But r1 plus r2 all squared is okay. So what I would observe is I would observe that I know r1 plus r2 squared is r1 squared plus r2 squared, which is the thing that I've got, plus 2r1 plus r2. So in other words, I can rewrite this equation, r1 squared plus r2 squared, to be r1 plus r2 all squared minus 2r1 r2. And actually that feels like that's got me somewhere, because I know from equation 4 that r1 plus r2 is r. So therefore r1 plus r2 all squared must be r squared. So let's substitute that back in. And what I find is I've got pi over 2 times r squared minus r squared plus 2r1 r2. And of course, what's critical here is I've got r squared minus r squared, which is great. And then I've got 2 lots of r1 times r2. Now, partly for space saving reasons, and so you don't have to have a third screen of maths. What I'm then going to do is I'm going to take equation 2 and equation 3 and substitute them into this equation here. So let's do that now. So if I take equation 2 and equation 3 and substitute them in, I'm going to get pi times a half r minus x. Again, what I've done is I've taken equation 2 and equation 3 and put them into here. And of course, a half times a half is a quarter, and r minus x times r plus x. Well, I know how to do this. I can just use difference of two squares, and that's going to give me pi over 4, half times a half is a quarter, r squared minus x squared, which from equation 1, I know is going to be 4. So in other words, I've got pi over 4 times 4, and that is just going to give me pi. Unbelievable. Just from something that wouldn't appear to get to this equation at all, I get the fantastically lovely answer, which as mathematicians we all enjoy, which is pi. And of course that makes sense. If you work your way through the maths, you can see why that should fall out. But it feels good to get to that answer, doesn't it? If you got there on your own, well done. It is very possible you've done it a very different way. That is, of course, is fine, but you would have set it up using fairly similar questions. Now, there is a very clever way of doing this, and by clever I mean quick. Did anyone else spot the quick way? So the quick way of doing the question. So I'm going to go all the way back to this diagram here. Now, what you'll notice about this diagram is, and I said it intentionally at the start of the question, is I said to you that there's a smaller semicircle and a larger semicircle inside the large semicircle overall. Nothing here whatsoever says the relationship between the small radii and the big radii. In other words, the radii of the small semicircle and the radii of the big semicircle. So why don't I just let them be equal to each other? So if I redo the diagram slightly, not the best diagram in the world, but I'm sure you know what I'm doing, whereby these two semicircles are the same, well, then I know several things. The first thing I know, because now this is the center of my large semicircle, I know my large radius is 2. And if I know my large radius is 2, it must be the case that my small radii, in other words, the semicircle of the same radii, and they're both equal to 1, I've got my number straight away. So when I have the same area equation, which is pi r squared over 2 minus etc., I plug in my numbers of 2 and 1, and nice and easily all falls out, and I get my pi again. Sometimes being sneaky and being clever will get you there. You have to be a bit careful that you're not losing generality, but in this case you're not, and it's acceptable. And if nothing else, this is a good check of what you've done. Either way, if you got to the pi, well done. Again, like I say, I mean, clickbaity headlines aside, it's a truly lovely question with a great answer. And even if you didn't quite get there, have a go through it again. It's a great question to ask someone else how to do. As ever, any comments down below, do like the video. It's one of my favorite questions, as I've said several times already, and I will be using it when I start with my new year this September. Like and subscribe, helps the channel grow, helps more people see the channel. I'll be back again for question 2 tomorrow. Thanks all.